this lesson is on graphing rational functions. You should take notes on this lesson in your notebooks, and you should use those notes as a resource when you start doing your homework that's associated with this lesson. Also, if you're viewing this lesson via VCR tape, feel free to stop the tape at any time. And when you start doing your homework, if you're viewing this tape while doing your homework, feel free to stop the tape at any time to play the tape back and what have you. Now, first of all, let's give a definition. Let's go over the definition of a rational function. Definition: a rational function is a function defined by a rational expression. That's what we mean by a rational function. A function that is defined by a rational expression. Now, we have discussed rational expressions in some of our previous lessons. We worked with rational expressions. We multiplied rational expressions. We divided rational expressions. We added rational expressions. And we also subtracted rational expressions. So we've had a lot of work with rational expressions, so we already know what rational expressions are. Rational expressions are sometimes referred to as algebraic fractions. So your function is defined by that type of expression. For example, f of x equals 4 over 3x minus 2. This is an example of a rational function because, as you can see here, we have a rational expression, or what we consider an algebraic fraction. Now, as indicated, a rational function is a function defined by a rational expression. An example, f of x equals 4 over 3x minus 2. You have x in your denominator, so that makes this a rational function. If I have f of x equals 5x plus 1 over 5, in the sense that we're discussing rational functions, this would not be considered a rational function because here x is in your numerator, but you don't have x in your denominator. You can have an x in your numerator and denominator. For example, if I have f of x equals 3x plus 1 over x minus 6, this would also be an example of a rational function because you have x in your denominator. It's a rational expression or algebraic fraction. Another example would be f of x equals 6x squared plus 7x minus 2 over 5x squared plus 6x minus 1. Another example of a rational function. As indicated, all of these are rational functions except this one. This would not be considered a rational function in the sense that we're using the term rational function. Because this really just reduces to a regular linear equation here. This would reduce to x plus 1/5. So that's just an ordinary linear equation there. But the types of rational functions that we're concerned with are the types that have x or some expression involving x in the denominator. So that's what we mean by a rational function. Before we can graph these rational functions, you need to know what we mean by asymptote. You need to know what an asymptote is. Definition: an asymptote is, and right here, an asymptote. An asymptote is an imaginary line that the graph gets closer and closer to. But never intersects. In other words, the graph gets closer and closer to this imaginary line, but it does not intersect or does not touch this imaginary line. That's what we mean by an asymptote. For example, if I have this function in the rectangular coordinate system, this might be an asymptote here. This function, this function here that I'm getting ready to draw, you'll see it getting closer and closer to that line, but it won't touch that line. If I keep on going forever to infinity, if I could go to infinity, then at infinity, at the forever point, it would intersect this imaginary line. But other than that, it does not intersect the imaginary line. It just gets closer and closer. So I have this function coming across here like this. It's getting closer and closer to that imaginary line. You see how it's getting closer and closer? As we go to the right, it's getting closer and closer and keeps on getting closer. You see? If I keep on going, though, even though in reality or theoretically in mathematics, it never touches that imaginary line. If I keep on going, it'll look like it's touching because in reality, we use instruments to draw our lines, and we don't have a microscope that we can see that there is still a difference between the graph and the imaginary line. So as you can see, this imaginary line here would be an asymptote. That would be an asymptote because this graph here, whatever it is, let's call it f of x. The graph of this function here, f of x, gets closer and closer to that imaginary line, but it never actually touches that imaginary line. I can keep on going way down here. I keep on going indefinitely to infinity, as we say, and it won't touch that line until I get to infinity, until I get to that forever point. So that's what we mean by asymptote. Now we'll be concerned with two types of asymptotes in this class. We'll be concerned about vertical asymptotes and horizontal asymptotes when graphing rational functions. And that's the reason that we're going into asymptotes, so that we can use the idea of asymptotes and use asymptotes to help us graph rational functions. Now, asymptotes don't have to be vertical or horizontal. They can be slanted or what we call oblique asymptotes. But there is an advanced lesson that we have on graphing rational functions, which is part 2 of this lesson on graphing rational functions, which takes up graphing rational functions that have oblique or slanted asymptotes. So feel free to look at that telecourse tape if you would like to study more advanced graphing of rational functions. But once again, as a class, we'll just be concerned with graphing rational functions that have horizontal and vertical asymptotes, not the ones that have oblique asymptotes. So with that said, now we know what an asymptote is. So when you're graphing rational functions, That's one of the things you have to do. You have to find the asymptotes, and then you have to find out how the function behaves when it's close to the asymptote. Is it decreasing? Is it increasing? How does it approach the asymptote? I show this function here approaching the asymptote from the left, but I could have very well shown a function approaching this asymptote from the left, you see. So it's very important when you're graphing rational functions to know whether it's approaching the asymptote from the right or the left, if it's a vertical asymptote, or if it's a horizontal asymptote, whether the graph is approaching the asymptote from above or below. So basically, when you're graphing rational functions, you find the asymptotes, which we're talking about vertical and horizontal asymptotes, because we're not going into slanted asymptotes once again. And then you just plug in points and find enough points so that you know how the graph will behave. So that's what we mean by the asymptote. It's just an imaginary line that the graph gets closer and closer to. So now, we need the steps involved in graphing these rational functions. First of all, step number one, when you're graphing rational functions, the first thing you have to do is reduce the rational function to lowest terms. You have to make sure that the rational function is reduced to lowest terms, and we discussed this in a previous lesson, reducing a rational expression. The rational function is defined by a rational expression. So to reduce the rational function, you just reduce the rational expression. So step number one, you must reduce. Make sure that the rational function is reduced to lowest terms. Reduce the rational expression. All right, step number two. After you reduce the rational expression, you have to find the vertical asymptotes. So that's step number two. Find vertical asymptotes. Now for your vertical asymptotes, to find those, you look at your denominator. After the rational expression is reduced, let me mention this also. Before you reduce, before reducing, you have to exclude values from your domain that will make the function undefined. Values that will give you 0 in your denominator. So part of reducing, prior to reducing, we'll say prior to reducing, you have to exclude values that will give you 0 in your denominator. Exclude x's, or values of x, exclude values of x that give 0 in the denominator. So you have to really do this prior to reducing. Before you reduce, you have to exclude values of x that will give you 0 in your denominator. So to do that, of course, you might have to factor your denominator if it's not already factored. Okay, so let's, in fact, let's make this step number one. Okay, and we'll make step number two, reduce. Okay, so step number one, we'll say exclude values of x that give 0 in the denominator, because dividing by 0 is undefined in the set of real numbers, and also in the set of complex numbers. Then you reduce. All right, then step number three, you find the vertical asymptotes. And the vertical asymptotes are x equals any number that will give you 0 in your denominator after the rational expression is reduced. That's what we have for the vertical asymptote. Find the vertical asymptotes. We put a S in parentheses. You might have one vertical asymptote or you might have several. So once again, x equals any number that will give you 0 in your denominator. Any number that gives 0 in the denominator of the result of step 2. Any number that gives 0 in the denominator, DEN for short, for the result of step 2. Okay, for the result of step 2. So in step 2, we reduce the rational expression. So we're talking about after the rational expression is reduced. If there's any number that would give you 0 in your denominator, then x equals that number would be a vertical asymptote. For example, an example of step 3, if I have this, if I have f of x equals 2 times x plus 3 over x plus 3 times x minus 2. Okay, if I have this, first of all, if I look at my denominator, I see that x cannot be negative 3, because if I have negative 3 here, I'll get 0 in my denominator, and x cannot be 2, because if I have 2 here, I'll get 0 in my denominator. So those are the values I have to exclude. I have to say that x cannot be negative 3, and x cannot be 2. I have to exclude those two values from my domain. So after I do that, then I can reduce this. Reduction, I can cancel that factor. So it would reduce to 2 over x minus 2. Now, when I get to, that would take care of steps 1 and 2. Step 1, I excluded the values that would give me 0 in my denominator because we can't divide by 0. Then I reduce. Step 2. Step 3, I want to find the vertical asymptotes. I'm looking at what I got after I reduced for step 3. I'm not looking back here to get my vertical asymptotes. After you reduce, you look at that. So I reduce, this is what I'm looking at, and I can see now that what would give me 0 in my denominator is 2, x equals 2. So that is my vertical asymptote. My vertical asymptote in this case for this rational function is x equals positive 2. That is my vertical asymptote. So I can really go ahead and draw my vertical asymptote on my graph for this rational function here. I would draw a rectangular coordinate system like so, and then I would just go over to the place where x equals 2, 1, 2, and I would draw an imaginary vertical line. And that is my vertical asymptote, x equals 2. So you have to find the vertical asymptotes, or asymptote. You might have 1, you might have 2, you might have more than that. Now, after you find the vertical asymptotes, then you have to find the horizontal asymptotes. So for step number 4, you have to find the horizontal asymptotes. Once again, step number 4, you have to find the horizontal asymptotes for the rational function. Now, to find the horizontal asymptotes, you have to look at the degree of your numerator and the degree of the denominator. That's what you have to look at to find your horizontal asymptotes. For part A, if the degree, you're making sure this is reduced, and you're looking at, let's say, look at the result of the reduction. Look at the result of step number 2. Okay, to find the horizontal asymptotes, we'll say A, look at the reduced rational expression. The result of step 2. Look at the reduced rational expression. Look at the reduced rational expression. Number 1, if the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptote. If degree of numerator is greater than or larger than the degree of the denominator, there is no horizontal asymptote. Once again, if you reduce the rational expression or the rational function, and you look at the degree of the numerator and the degree of the denominator, and you find out that the degree of the numerator, after you reduce, if the degree of the numerator is larger than the degree of the denominator, that means that there is no horizontal asymptote. So you don't have to worry about a horizontal asymptote if that's the case, because there is none. You just work with the vertical asymptote or asymptotes that you have. So that's scenario number 1. Okay, the next scenario, an example of this scenario here would be something like f of x equals x squared plus 7x plus 12 over x plus 5. If I look at this, my numerator, the degree of my numerator is 2, and the degree of my denominator is 1. So 2 is greater than 1. My degree here is greater than my degree there. So of course this can't be reduced. So that means that it's already reduced to lowest terms. So that means that there will be no horizontal asymptote for this rational function. Okay, for number 2, if they are the same, okay, if the degree of the numerator is the same as the degree of the denominator, this is after you reduce the rational function to lowest terms. If after you reduce the rational function to lowest term, if the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is the coefficient of the numerator, the leading coefficient of the numerator, y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So it's important that you make sure your numerator and denominator both are in what we call simple form or standard form for a polynomial. Make sure you have the highest degree term first, the next highest degree term on down to the constant. So once again, for number 2, if the degree of the numerator, and we'll use NUM short for numerator, is equal to the degree of the denominator, DEN for short, the horizontal asymptote or asymptotes, you might have more than one. The horizontal asymptote will be y equals the leading coefficient of the numerator, which is the coefficient of the highest degree term of the numerator, divided by the coefficient of the highest degree term of the denominator. That would be equal to the coefficient, which is called the leading coefficient. Coefficient of highest degree term in the numerator divided by or over coefficient of the highest degree term in the denominator. Once again, if the degree of the numerator is the same as the degree of the denominator, the horizontal asymptote or asymptotes will be y equals the coefficient of the highest degree term in the numerator divided by the coefficient of the highest degree term in the denominator. And we're only going to have one horizontal asymptote. There's only going to be one because there's only going to be one coefficient of the highest degree term in the numerator and only one coefficient of the highest degree term in the denominator. So you're only going to get one number when you divide those two numbers. So that means that there's only going to be one horizontal asymptote. So what we said before about you might have more than one horizontal asymptote would not be true. Because you can see that you're only going to have one number for each one of those, and when you divide those two numbers, you only get one number. So that means that you only have to worry about one horizontal asymptote. So this makes it pretty simple when you're dealing with the horizontal asymptotes, because unlike the vertical asymptotes, you can have several, but the horizontal asymptotes, you can only have one. So you have none. You have one horizontal asymptote. Okay, if the degree of numerator equals to the degree of the denominator. An example of this case, and then we'll look at what happens when the degree of the numerator is smaller than the degree of the denominator. An example of this case would be alpha of x equals x squared plus 5x plus 6 over x squared plus 10x plus plus 25. Okay, that would be an example of what we have in this case. The degree of the numerator is 2. That's the degree of the numerator. Okay, the degree of the denominator is also 2. Degree of denominator. They're the same. The degree of the, and this is already in lowest terms. If it can't be reduced, it's already in lowest terms. So the degree of the numerator and the degree of the denominator are the same, but you have to make sure it's in lowest terms first. Of course, I know this is in lowest terms, so we don't have to worry about that. But if that's the case, then in this case, there is a vertical asymptote. And the vertical asymptote, the coefficient here is 1, the coefficient here is 1. So it would be y equals, not vertical asymptote. I said vertical, but I mean horizontal. Okay? Not the vertical asymptote. Okay, vertical asymptote, you have to look at what will give you 0 in your denominator. Okay, so this should be horizontal asymptote. The horizontal asymptote will be y equals 1 over 1, which is y equals 1. That would be the horizontal asymptote. So, so that would be the line that the graph will get closer and closer to in this case. So I think you already know how to graph these asymptotes. You graph them just like you graph any other line. Horizontal asymptote will go straight across like that. So you would go up to a place where y equals 1, which is right here. You would draw an imaginary line. You see, that would be that horizontal asymptote. The graph of that horizontal asymptote. Okay, so there's one more case to consider. If your fraction is reduced to lowest terms, and we'll call this number 3. If the degree of the numerator is less than the degree of the denominator. If the degree of numerator is less than or smaller than the degree of the denominator, for the reduced, okay, for the reduced rational function, then the horizontal asymptote is y equals 0, which is the x-axis, which is the x-axis. Once again, this is the last case that we have to consider in this class, because we're only concerned about vertical and horizontal asymptotes. If the degree of the numerator
is smaller than the degree of the denominator for the reduced rational expression. So you have to make sure you reduce your rational expression. Then the horizontal asymptote is y equals 0. It's the x-axis.
This is the conclusion of this introductory lesson on rational functions. In the next lesson, we'll look at some examples. Once again, this concludes this lesson. In the next lesson, we'll look at some examples.